So when we're talking about light being emitted, when my electron is going from an excited state to a ground state, we want to talk about, well, what does that look like? And so we were able to find a spectrum of it. And so we're going to talk about what it looks like. It's an emission spectra, and then there's two different types of emission spectra. There's line spectra and there's continuous spectra. And I'll show you an example. All right, so what's an emission spectra? So the light emitted, when my electron goes from the higher excited state to a lower. So the light emitted either as a continuum or in discrete. Can't write today. There we go. Discrete lines by a substance in an excited state. So the light emitted by a substance in an excited state is either going to be a continuum or it's going to be in discrete lines. So those are the two types of emission spectra we can get. Now you're actually used to seeing continuous spectra. So continuous spectra is when all wavelengths of visible light are present. So an example of a continuous spectrum would be, say, for example, the sun. So when we're looking at the sun, or not looking directly at the sun, but when we see the sun, we don't see different colors. Now, sometimes you might, and that's when you think about a rainbow, okay? But in general, it's just all one. That's when all those wavelengths, they're present, but we don't see it separated out. We know they're all present because when they do become separated out through a rainbow, because the light has hit a prism, so usually it's rain or something like that in the clouds or in the air, hits the raindrop, acts like a prism, and then that's what separates my line, my continuous spectrum, my sun out, and that's what makes it a rainbow. And so a rainbow is kind of like a line spectra, okay? So the sun is a continuous spectra, and then we can actually make it into a line spectra. But the sun would be an example. Another example would be whenever I talked about a heated object. And so say we were to heat up our stove, and the stove top there, the heating coil turns red. We don't see a bunch of red lines like this, we just see red. So it's a continuous spectrum. It has all the wavelengths present, but one wavelength is gonna be in more higher abundance than the other ones, okay? So when you're not seeing lines. So most of the time we're gonna see continuous spectra, but we can see a line spectra. So a line spectra is the emission of light only at discrete wavelengths. So if I have some atoms and I heat them up, say it's a solid. When it's a solid, I heat it up and I excite the electrons, and then when they cool down, they're going to emit a continuous spectrum. But I can actually take some atoms, and instead of them being a solid, I can put them in the gaseous state. So whenever they're in the gas phase, they don't produce a continuous spectrum. Instead, they're going to produce bright lines that are going to be distinct parts of my visible spectrum. And whenever we're talking about this, we're talking about the visible. So here would be my white light spectrum. So think about this as just like the sun or anything like that. Okay, so it's a continuous spectrum. But say I take helium or barium, I put it in a tube, it's a glass tube, and you can see this in the lab videos. And so take these glass tubes and I heat them up. So then I take the electrons, when I heat them up by turning on the electricity, so the electricity flows through them, then my electrons go from the ground state to the excited state, and then it's very unstable, they can't stay there. So then they're gonna drop, and then other electrons are gonna keep going. So it's kind of like a little cycle. So they'll be here, they go to the excited state. This is very short-lived, unstable. It'll drop down really quick, and when they release, we will see the colors, okay? So you can actually look at this. So if I were to heat up something, I could take a spectroscope, I can look at a spectroscope on whatever that glass tube is, and I can actually see the line spectra. Now, if I'm just looking at the spectra, looking at the heated up, it's gonna kind of look like a neon tube, like the neon lights. So you won't see those lines as distinctively. So I could collect my emission spectra and I could see these are the lines. And whenever I see the color, these colors actually correspond to specific wavelengths, and then those wavelengths correspond to specific energies, because remember we have that equation that relates the two. And so I can actually go through and figure out, okay, how many lines would I have, and then what are the colors. Now each one of these lines corresponds to a specific energy drop. So if it's dropping from, say, n equals 3 to an n equals 2, this is a specific amount of energy. And that energy is going to be from a 3 to a 2 is different for each element. So how many different options it has to drop determines how many of these lines you have. So barium has a lot more options. It can drop from an excited to a lower. So it could go 3 to 2, 3 to 1. It could go 4 to 3, 4 to 2. Like going from a higher to a lower, there's a lot more options for barium than it is helium. And you know this because there's a lot more lines in the barium than the helium. You're going to see this a lot more when you do your lab. So then the question would be, well, how do I actually figure this out? Okay, so it's going to be hard for us to actually calculate this amount of energy. The light comes out, but all we know is the wavelength. So I know that the wavelength is associated with this energy, but I don't know the energy. All I get is this emission spectra. And on most of these, there's going to be wave numbers underneath this, so I can figure out what the more precise wavelength is of this. So if I have this wavelength, what if I want to actually know the energy difference, or what if I actually want to know what that emission drop is? I can actually calculate those based on the n. So if I know the color of the wave, I can figure out the n drop. Or if I know the n drop, I can use these n differences, I know it's n equals 3 to n equals 2, to figure out what the wavelength and what color my light should be. And so on the next lecture, we're going to talk about what is that equation that helps us to figure out what the energy drop is and the wavelength.